Okay, so today we are looking at as a grid, logarithms, and exponentials. Exponential functions. So step by step, we start with exponential. Exponential functions. In exponential functions, we are starting with the graphs, sketches. So I want to see, the first thing is how to sketch exponential functions. And then our second thing will be logarithms, how to sketch logarithms. So we take them as examples here, starting with 1, sketch 1 u is equal to 2 to the power x. That is u. 2 v is equal to 2 to the power negative x. 3, we'll sketch w. W is equal to negative 2 to the power x. And 4, z is equal to negative 2 to the power negative x. So I want to sketch these 4 functions and see how far we go. So start with the first one. So I'd love to put them on one sketch. So let me bring them here. The first one is u is equal to 2 to the power x. So we use a simple table. You know, when you're sketching any function, if you want, you can use some table where you get the x values and then you get the y values. In this case, we are calling y to be u. So let's use negative 2. Let's use 0 and positive 2. And then, since we also have 2, which is 2 is v is equal to 2 to the power, v is equal to 2 to the power negative x. We'll also find v using the same values of x. 3, we got w is equal to negative 2 power x. W is equal to negative 2 power x. We also get the values of w using the same values of x. And 4, we have z is equal to negative 2 to the power negative x. So also get the values of z here. And then we'll have our sketch here. We'll have our sketch just here. So we'll have this sketch here. Okay. So if we need space for working, we can be going to and fro. Okay, so let's start with u. So u is equal to 2 to the power x. So what is u when x is negative 2? Now we all understand that the negative power is just telling us that the whole thing is happening in the denominator. Meaning we have 1 over 4. So u is 1 over 4 when x is negative 2. So we have negative 2 here. We have 0 and we have positive 2. Like that. And so when we have this, we have found so far 1 over 4. So we have a point there. What is u? What is u when x is 0? So we have 2 to the power 0. Now n number to the power 0 is 1. So we obtain 1. And so we have 1 against 0. What is u when x is 2? 2 to the power 2 is 4. So we have 4 when x is, so this is 1. Now we have 4 when x is 2. So if you look at this function 2 to the power x, for any value of x, this function will never be 0. That means that we'll have the sketch of our function showing that it will never touch 0. You never touch the x-axis and then going in that way. So it's a curve, and we label it u is equal to 2 to the power x. Okay, so we're emphasizing that for any value of x that we place there, the fact that 2 is not 0, we can never get 0 as our u. That's why this x-axis has become an asymptote in this matter. Now, an asymptote, normally, we denoted it using dots. But for the x-axis, we just, if you want, you can even show that my graph will never touch there. There's no harm. The second one, let's go to the second one, v. What is v when x is negative 2? So we have v is 2 to the power negative x. So we still have a negative, and then x is coming with its own negative. So we'll have 2 to the power 2, which is equal to 4. So we get 4 here. We get 4 here. And then, what is v when x is 0? So negative 0 is the same as 0, giving us 1. So we get 1 even here. What is v when x is positive 2? So remember, the negative is just telling us that everything is happening in the denominator. So we'll have 1 over 4. So we get 1 over 4. And so we have negative 2, 4. We have 0, 1. And we have 2, 1 over 4. Again, for whatever value of x v will never be 0. This means that our graph can now be sketched in this manner. Indicating that it can never touch the x-axis. So this graph we have is v is equal to 2 to the power negative x. Again, what is w? What is w? What is w when x is equal to negative 2? Now, one thing we must note here is that negative 2, the negative is not being affected by the power. So it is negative, as the negative to the power is just telling us that everything is happening in the denominator. So we get negative 1 over 4. So we have negative 1 over 4. What is w when x is equal to 0? We get, not 2 to the power 0 is 1. So we'll have negative 1. So we get negative 1. And what is w when x is equal to 2? So 2 to the power 2 is 4. So we'll have negative 4. So we have negative 2, comma negative 1 over 4, 0, comma negative 1, and 2, comma negative 4. So we have a point here. We also have a point there. And we have a point here. So our sketch is of this nature. Again, the graph will never touch the x-axis because this function can never be 0 for any value of x. What about z? So we'll have z is equal to negative 2. When x is negative 2, we'll have negative 2 there, telling us that we have negative 2 to the power 2, giving us negative 4. So we get negative 4 there. And z is equal to negative 2 to the power negative 0, which is negative 1. So we have negative 1. And z is equal to... Hello.
Isn't negative 2 to the power 2 4?
The negative is not part of the power, so it still remains negative 4. You only get worried if the function comes in this form. That's when it becomes 4. So the negative is just moving on its own. Is that okay?
Yes, sir.
So we have negative 2 to the power negative 2. That is when x is 2. But this is the same as negative 1 over 2 to the power 2, giving us negative 1 over 4. So we have negative 1 over 4 against 2. So negative 2 is giving us negative 4, and then negative 1, and then negative 1 over 4. So our sketch is going to be of this nature. Again, it will never touch the x-axis because this function is never going to be 0 anyway. So this one is z is equal to negative 2 to the power negative x, and this one is w is equal to negative 2 to the power x. That way. So these are the four families for all the exponential functions that exist in this world. So these are the shapes that you're going to be having for all the exponential functions. Whether there will be shifts or any addition of any kind or any multiplication to this function, the shape will still come out this way. You shift it as it is, you stretch it as it is, everything you do will be as these functions are. So this table here is, you only get to this table in an exam if you have forgotten the family, the shape of the family. Is that a question? Can I see the one? Chiru. Okay. So what I was saying is that you only get to use a table of values in an exam if you have forgotten the shape of the function that you are dealing with. This means that the family remains the same, the shape remains the same, even if y, or let me use the same u, even if u is to be equal to e to the power x, you sketch the same graph. The only thing you do is you remove -2 and +2. 0,1 remains there. If you check in your calculators, you'll notice that e is actually a whole number. I mean, it's actually a decimal number, which is 2 point something. So it's just a number. It's just some number. It's just a constant. Just like 2 is a constant. Meaning, this is the same function. You sketch it the same way, even if there was e there. It will be the same graph, even if we had e here. It will remain the same, even if z was -e to the power -x. The shape will come out the same way. The only thing that will remove is 2 and -2. 0,1 remains there. 0,-1 remains there for each of these graphs. So let's see varieties of questions of this nature.
So I have a question.
Okay.
So when sketching, even if they've given us any number, for example, they've given us the power x, the power w, whatever, but are we supposed to bring out our values like the way you did, -2, 0, and 2, or we can just use them always?
No, these are just your aid, just to guide you on how your sketch should look like. Otherwise, if you know the shape of that family, you can as well just work out the shape and then move on. Just place the shape, no working.
All right, so thank you.
Okay. So we are saying we had examples 1, 2, 3, 4. Let's have another set of examples, or we just add, we say example 5. We are still sketching. Now we are sketching y is equal to 1 plus e to the power x. So 1 plus e to the power x. Now, we have already seen that e to the power x falls in which family? In this family. There's just an addition of a constant. In trigonometry, we called it a vertical shift. It is still called by the same name, even in these functions. So what will happen is that the same way we treated the 0, y is equal to 0, which is the x-axis, as an asymptote. When you add the 1, it means that you'll be adding a 1 even to the x-axis. So the asymptote will move. Since we are saying that e to the power x will never be 0, it means that you will never get 1. Remember, you can only get 1 if this piece can be 0. So that we say 1 plus 0 is 1. But this will never be 0. You will never have 0 here. For any number x, e to the power of that number can never be 0. This means that we'll never have a 0 from e to the power x. So we'll never have 1 as y. So how do we sketch our function? Our function will be sketched. Since we know the family, the only thing we are doing is to the 0, which is the x-axis, we add 1. So this number will always be our asymptote. So we have a new asymptote now. Instead of dealing with x as the asymptote, as the original questions were, as the original family caves were, now the asymptote has gone to 1 because we have added a 1, a whole number 1. And then you solve for the y-intercept. If you want, you say, you know the y-intercept is always when x is 0. So you substitute 0 for x, and you notice that e to the power 0, even if I don't know what e is, e to the power 0 is 1. So we have 1 plus 1, which is 2. So the intercept is now at 2. Remember, this is 1. And so your graph comes out in this manner. We call it a shifted graph of an exponential function. So what are we taking note? We are saying the asymptote will always be the vertical shift, or will always be the constant added or subtracted to the initial exponential function. Like that. Another example, 6, y is equal to -2 plus e to the power -x. Now, e to the power -x What family? Let's look at the family. E to the power negative x will fall in the family of v, where v is equal to 2 to the power negative x or e to the power negative x. So the curve goes in that direction. So from this note, the asymptote, so we are sketching what is the asymptote, the added or subtracted. So we have negative 2. So negative 2 becomes our asymptote. Negative 2. Then from there, we go back to the function and look for y when x is 0. We're looking for the intercept. E to the power negative 0. This is the same as negative 2 plus e to the power 0. E to the power 0 is 1. So we have negative 2 plus 1 giving us negative 1. So the intercept is negative 1. And how is the family? The family of functions is this one. So we'll learn how to get the intercept for x when we do logarithms. For now, we suspend it just like that. We know we have an intercept there that needs to be found. So once I know the family of, once I know the shape for the exponent that I have, I can now attend to the added or subtracted constant. Just to move the asymptote. Okay, what happens if the power also has an addition? Let's see. Example 7.
Sir. Hello, sir.
Hello.
On the negative one there, on the x-axis, or what value is where the graph is passing?
So we're saying we'll calculate it later when we look at logarithms as well.
Oh, okay.
So for now, we assume we don't know it. So 7, we want to sketch y is equal to, say, e to the power x plus 1. E to the power x plus 1. So we do it each shift at a time, and then we'll combine the shifts and see what we get. So what happens if y is equal to e to the power x plus 1? This guy looks like, or it is actually affecting the x values. So this added constant was affecting the y values, but this one is affecting the x values. So it will affect the intercept. The intercept always used to be, once we say x is 0, we could get 1, and then we make it our intercept. But this time around, x can be 0, but we still have e to the power something, which needs to be calculated if we knew what e is. Meaning, we'll get the numerator, we'll get the power x plus 1 and equate it to 0 as our first step and get the value of x. So we get negative 1. And look for the function, look for the value of y when x is negative 1. We know negative 1 plus 1 is going to be 0, so get 1. So what does that mean? When you sketch, so the asymptote has not been touched. It is still the x-axis. the family of curves, the variable x is positive. Here we have to be careful. You don't look at the sign of the constant that is being added. You look at the sign of the variable x. So the variable x is positive. So when the variable x is positive, the family is for the positive values of x. This is the family. So this is the shape that we are dealing with. For example, 5, or the shape for u. The power is positive. This means that now we have a point -1 is the one that is giving us a 1. So we have 1 there from that guy. Okay? So now what happens at x, when x is equal to 0, what do we get? When x is 0, we get e to the power 0 plus 1, which is equal to e to the power 1. So we have e power 1, meaning it has to be on top there, e to the power 1, which is just e. And so we'll sketch our function in this manner. So remember, we always need to know the intercepts. So this means that even if you forgot to do this, it's still okay, because once you take x is equal to 0, that is the important point, the intercept. So you can have your sketch even if I don't have anything to do with 1. It's still okay. You just need to show that you understand that there's a shift. And that's why you're telling us where 1 has moved to. Because we know in the original graphs, it requires that 1 be the intercept, 1 or -1. But for this case, we are seeing 1 not being an intercept. So if you so wish, you can state where 1 has gone to show that you understand what you're doing. So what happens if we had a function f of x, which is equal to 3 plus e, or should I put a minus now? Let me put a minus now. Minus e to the power 1 minus x. Now I need to know the family. The power x is negative to start with. The e itself is negative. So you go and look for the family where you have two negatives, negative for the base and negative for the power. It is the function z. So that is the family that you're going to deal with. The curve is going in that direction. So now, after knowing the family of curves, you understand that there's a shift. Okay? There's a shift by 3. So 3 is automatically going to be our asymptote. So 3 becomes the asymptote. Then we know the shape. Then now you go to what happens when x is 0. What is f of 0? F of 0 is 3 minus e. That is where it will cross the x-axis. I mean the y-axis. Now you understand that e is 2 point something. So 3 minus 2 point something is a positive number. So the graph will be of this nature. Crossing at 3 minus e. This value here, we'll know it later. Remember what I said? Hello.
I think I'm lost here. Here we did not equate your 1 minus x to 0.
So we did, because I wanted to show you that even if we have forgotten to do this, you can still have your sketch.
And then the 3 minus when we say f of x is equal to 0, 3 minus a, we do not include the 1 minus x.
It will be 1 minus 0, is it?
Yes, which is negative 1.
Which is positive 1.
Or positive 1.
And what is e to the power 1? It's the same as e.
Okay, sir.
Yes. Now, sometimes examiners will ask you to sketch two graphs on the same sketch. So for such purposes, you are advised to indicate the function you have sketched. It's only necessary to indicate if you have more than one graph on the same sketch.
Sir.
Hello.
Yes, sir. Should the graph cross the x-axis?
It's free.
Huh?
For as long as there's a shift, yes.
It's okay.
It's okay.
Yes. So like for now, okay, it's fine, sir. Go ahead.
All right. Okay. Another scenario is example 9. We want to sketch g of x.
Try to go back to the previous page. Thank you.
Okay.
It's okay.
So I want to sketch g of x is equal to negative 1 plus 2 e to the power 2x minus 4. Look at this function. There's so many numbers everywhere. So what do? We must know that 2 is independent of the power. Okay? This is how best we understand why negative 2 to the power 2 is still negative 4. Okay, because if I have negative 3 multiplied by 2 to the power 3, automatically the negative 3 will be here. The 2 to the power 3 will get to 8. And then that's when I'm going to multiply now. Negative 3 times 8, negative 24. So the negative will still be there. Okay? So I was just trying to make a point here that the 2 is not affected by any power, as we can see. So this means that the one that holds the family of the curve is e. E to the power 2x. So 2x is positive. The e itself is positive also because its e coefficient 2 is positive. So we are dealing with a positive case, which is the first graph that goes. So which family are we dealing with? We are dealing with the family of example 5, which is the family of u. So now that we have the family of u, we say that any added number becomes the asymptote. So we keep our words. We are operating like body. So we have negative 1.
And you're operating like body, sir. The things are yet to be fulfilled.
Okay, so we have negative 1 as our asymptote. And then what happens when x is 0? I want to know where to cross the y-intercept, the y-axis. When x is 0, we have g of 0 is equal to negative 1 plus 2 e to the power negative 4. Okay, this is going to be -1 plus 2 over e to the power 4. Now e is 2 point something, so 2 point something power 4 is bigger than 16. So 2 over 16 is 0.00 something. So this number will still be negative. And so the family of curves goes up. So this is going to be our graph, where this guy is -1 plus 2 e to the power -4. We will know later how to find that intercept. We just found for y. And this is our graph. So the 2 has an effect on the y coordinate, on the y-intercept. This number which is being multiplied here, it stretches the graph. But because we're not drawing to scale, we are free not even to show that there was any stretching. No one will sanction us. Okay, so we had so much on exponentials.
Sir,
Hello.
now what about if there's no figure like any number which was added like in terms of the function? They all have -1. So it means there is no asymptote.
If there is no -1, it means that the asymptote remains the x-axis, like example 7.
I can't see the asymptote in example 7.
So the asymptote is not, you can't see because it's drawn on the x-axis. So the reason why the graph is not touching the x-axis is because the x-axis is an asymptote.
All right, thank you.
Okay. So we showed it. I noticed you joined a bit late. We showed it on this initial graph. So we said that this x-axis here is called the asymptote for all these graphs. And then in the example, we saw that the asymptote could move depending on the number that is added.
All right, thank you.
Okay.
So if there's no constant, then the y-intercept is always going to be +1 or -1 if there's no constant.
So if there's no constant, now the y-intercept will be -1 or +1 if there's no any shift. 1, there's no constant being added. 2, the power is free, it's just x. If there's a constant, it's no longer 1. If the power has an addition, it's no longer 1. Or any subtraction, it's no longer 1. Okay. Now let's look at another set of examples.
Sir,
Hello.
I have a question. I still don't understand. I don't get why our -1 plus 2e to the power -4 is placed beside on the x.
Still don't get why.
X-axis.
So here is it. Y is -1
On the positive
plus.
side of the x-axis.
-1 is for this intercept here. The -1 plus 2e to the power 4 is for the y-intercept and not for x.
Yes, if it's for the y, then why is it being placed there?
So it's just a matter of space. Otherwise, I'm writing it for this part here. -1 plus 2 e power -4.
Oh, Okay, yes, okay.
Uh-huh. All right. So let's now move to graphs, logarithmic graphs. Logarithm graphs. That is part 2 now, where we say how to sketch log functions. Now, log functions, we also have 4 families of their sketches. But one thing that is very, very important is to understand the relationship between log and exponentials. So if you have y is equal to 2 to the power x, and if I have log 2 y is equal to x, from this guy, I directly have this one. So whenever I have log base, the base can be written as a base is 2. You leave y, you go to the x. That x becomes the power for the base, must be equal to y. That is how logs and exponentials are related. And this relationship is called inverse of each other. So we say exponentials and logarithms are inverses of each other. So what does this mean? Since you are saying y is equal to 2 to the power x, and you are talking of them being inverses, this means that if in log 2, where there is y, we take 2 to the power x, we must still get x. So how possible is that? Log should have a property that allows it to drop this power here, so that we have x log 2, 2. This is 2 equal to x. How possible is this? How do we get x if we have log 2, 2? This should mean that log 2, or you can even get it by calculation. Let's say, okay, let's divide x. So what if we
Okay, sir,
divide
to be
x?
honest, I'm a bit behind there.
On which page 6 or before page 6?
The very same one that we are on.
Okay, don't worry. So if we divide x and divide x here, you will notice that we're going to have log 2, 2 is equal to 1. So whatever I've done here will come back later as properties of logarithms and exponentials. For now, we want to just understand one thing. How do we move from logs to exponentials if we want to deal with exponentials? That's a question we must answer here. So we are saying, if you have a log to any base, y is equal to x. If you have this, from this, you can move to exponential by getting the base. We read it as log y base a is equal to 16. So the base a can be written as a base 2. The x after the equal sign becomes the power to the base, and you get the y that is inside there. So this is an exponential and log relationship. And we call it an inverse relationship of logarithms and exponential functions. This is what we must get from this page. You can be asked in an exam to write this as an exponential. Log v base 7 is equal to p. Write it as an exponential. You will say in exponential form, this is v is equal to 7 to the power p. And you get all the marks. Is that okay?
Yes, sir.
Now that we are saying we can move from logs to exponentials, and if we have understood how to sketch exponentials, then our work will be easy as we sketch logarithms. So let's go to the sketches of logarithms now. We'll call them examples.
Excuse me, sir.
Okay.
You didn't finish that part where you started for log 2 to the power x is equal to x.
One way I was driving the one and the like.
Not really. It was another one, the one you're saying, log 2 to the power x is equal to x.
Okay, so I suspend that one. I said for now, let's just look at how we can move from log to exponential so that you're able to sketch them. And then we'll get back to the properties of logs and exponentials. And then we'll move to equations. Then the topic will be done.
All right, sir.
Okay. So we sketch 1. Y is equal to log 2x. So I want to sketch this function. Now we have no idea of what logs are. The only thing that we know is that we can move from logs to exponentials. So let's try to move. So this means that we can write this guy as 2 to the power y is equal to x. And once we have such an equation, it means that we can use a table like we did for other functions, except that this time around, we'll have to know the values of y and look for the values of x. We can have another function 2, y is equal to negative log 2x. Now, we didn't have any negative there in this relationship, remember? Everything was positive for it to work. So what do? The first thing we can do here is to divide by -1, divide by -1. So our function becomes negative y is equal to log 2x. Now that the log is positive, we can write it as 2 to the power negative y is equal to x. So I have a second function.
So you said, how did you find x in the first question?
So we are saying from this relationship here, as we are starting from, we can raise a to the power x and it will be equal to y. What does that mean? We can raise 2 to the power y and it will be equal to x. We can raise 2 to the power negative y and it will be equal to x. Is it okay?
Yes, sir.
Good. 3, we can have y is equal to the log of 2 to the power, of 2 negative x. Here, we can raise 2 to the power y. It will be equal to negative x, the inside thing. So that if we divide by negative 1, divide by negative 1, we'll have x is equal to negative 2 to the power y. And 4, y can be equal to negative log 2 negative x. So that we first divide by negative 1, we divide by negative 1, our function will look like negative y is equal to log 2 to the power negative x, and then raise 2 to the power negative y is equal to negative x. Divide by negative 1, divide by negative 1, x is equal to negative 2 to the power negative y. So we have 4 functions, the same ones that we had for exponentials. They have come back for logs, except that they have done a switch. The variable that we can get values for is y, and then look for x. Okay? So don't forget, here the initial function is y is equal to negative log 2x. Here the initial function is y is equal to negative log 2 negative x. So we have 4 functions. Now I want to sketch them. Okay? Remember I said we can look for the values of y and get the values of x. So let's do it systematically like we did for exponentials. So they are all y's. So let's just differentiate them. So let's say this is y1, this is y2, this is y3, and this is y4. So on the table, we'll have x1, we'll have x2, we'll have x3, and we'll have x4. So we'll be looking for x1, we'll be looking for x2, we'll be looking for x3, we'll be looking for x4 after having the y values. So the numbering of the y's will come when we have sketched them. So I want to use the same numbers. This time around, they are the y values. So we're using -2, 0, and +2. But these values are for y. We want to obtain x1, we want to obtain x2, we want to obtain x3, we want to obtain x4. And then we'll have our sketch. So the sketch will be put here. This is where I'll put the sketch. So let's start. The first one, x1 is equal to, what is x1? x1 is 2 to the power y. Is 2 to the power y. Now, what is x1? when y is equal to -2. This guy is going to give us 1 over 2 to the power 2, which is 1 over 4. So we have 1 over 4. What is x1 when y is equal to 0? We'll get 1. So we have 1. And what is x1 when y is equal to 2? We'll get 4. So y is known. We have y -2, 0, and y +2. We are getting 1 over 4 for x. We are getting 1 and 4. So for -2, we have gotten 1 over 4. For 0, we've gotten 1. For 4, we've gotten 2. So if we sketch our function, again, this function, if you look at it, x1 can never be 0 because 2 is positive. It's non-zero. And for whatever value of y, you can never get 0. Even if y is 0, when y is 0 itself, we'll get 1. So you can never have 0 in this case. Meaning that x can never be 0. Remember, x is 0 on the y-axis. So we never touch the y-axis. So the y-axis is our new asymptote. The y-axis is an asymptote for these graphs. Just like x was an asymptote for those graphs, here it is y which is an asymptote for these graphs. Okay, so this graph is for, if we go back to our y1s, this graph is for y1 is equal to log 2x. So let's go back and look for x2. So what is x2? x2 is a function 2 to the power -y. 2 to the power -y. So what is x2 when y is -2? We'll have 2 to the power 2, which is equal to 4. So we're getting 4 there. What is x2 when y is 0? So we'll have 2 to the power 0, which is 1. So we'll get 1. What is x2 when y is equal to 2? So we'll get 1 over 2 to the power 2, which is equal to 1 over 4. So we have 1 over 4. So we have -2, 1 over 4. I mean -2, 4, -2, 4, 0, 1, and what else? 1 over 4, 2. So we have a point there. And then you can sketch this guy. Still sharing the same asymptote. This is our graph. So this is y2 is equal to, let's go and look at the log form of it, negative log 2x. Negative log 2x. Another one, what is x3? So what is x3? x3 equation is -2y. -2 to the power y. So what is x3 when y is -2? We get -1 over 2 to the power 2, which is -1 over 4. So we have -1 over 4. So -1 over 4. So what is x3 when x is 0? I mean, when y is 0, we get -1. So we have -1. So we have -1. And then what is x3 when y is 2? We get -4. So we have -4. And so you can sketch. We have -2, -1/4. We have -1, 0. And then we have -4, 2. So the function is going to have the same asymptote. So it's a function of this nature, like that. So this is y3, which is equal to log 2 -x. Another one, we're looking for x4 now. So what is x4? The equation of x4 is -2 to the power -y. -2 power -y. So what happens? So what is x4 when y is -2? So we have -2 to the power 2, which is -4. Excuse. So we get -4 here. So as we have followed the pattern, you understand that here we're supposed to have -1 and then -1/4. So we'll have -2, -4 here, and then -1, and then 2. So we sketch. This guy is going to have this curve, still keeping the same asymptote. So this is y4 is equal to -log 2 -x. So the same statement we made about exponentials, the same statement will be made about logs. This is the same graph if they said solve for y is equal to log ex. This will be the same graph if they said solve for y is equal to -log ex. This will be the same graph if they said solve for y is equal to log -x. And this will be the same graph if they said y is equal to -log -x. It will be exactly the same. This means that if there are any shifts, we will still be able to take care of the shifts using exponentials. That is, before you solve any question, it's your first question to solve under shifts or logs, you go back to exponentials. But as you keep solving them, you stop going back to exponentials. You just know that, oh, if I have a number here, it's just the same as having a number that one on the exponential. So I don't even need it. I just sketch it. So how is it? I want to bring in more examples now. Hope you still have the energy. Silence is acceptance. Okay. So let's go to, this was 1, 2, 3, 4. Let's move to 5. Example 5. We want to sketch f of x.
Sir,
Hello.
your power is gone. Just in the
Yeah?
yeah, power is gone. Just rest.
Ah.
Started sleeping. Like you're singing Kalarabai.
But we try to go through what we've learned today.
So I can continue.
Yes, sir, this is too much to take in.
It's like kirengirira kurefti sirefu minako.
Continue, sir.
Fila wanoka lero.
Continue with what
Okay,
is that?
guys.
Boy,
I don't.
MS boy
I don't.
anchita boy. Nikalina vambi.
It's a blown exercise, boy.
Kwesa kuingenera nona mwangati boy ka topic nkafupi kanji chenderera.
Abantu balira always class, boy.
Okay, so we'll suspend it here so that we have the energy.
Body.
You can stop recording.
Understanding.
Body.
Si vinto.
Sam, I can see the
I
previous
think
board.
Barry will fix it.
Oh, sir, you can stop the
Mama na
recording.
wasa, you have stopped.
It was. Yeah.